Apologies, that video was not supposed to get cut off that last time, but anyway, here we go. We're example 4, we're going to find a vector equation and parametric equations for a line segment that joins 2 points. Last chapter I did give you a shortcut for this, and I told you I probably don't use this shortcut much, so that's why I'm just going to write it down for you, is that we have a quick way of finding this that is always going to have our values of t go from 0 to 1. You could reparameterize this and you can come up with different equations that'll involve different values of t. We can parameterize it kind of however we want, but this is generally our easiest way. And if I kind of go through the work instead of using that shortcut, here's my option. If we can find a vector AB, so from point A to point B, -5 minus 1, 1 minus -3, and 7 minus 4 gives us our vector -6, 4, 3. We can take our initial point for our vector function r, which is going to be 1, -3, 4. We're going to take that vector that points at that point and add it to our vector multiplied by t in the direction we need to go, -6, 4, 3, giving us our vector function 1 minus 6t, the first component, -3 plus 4t in the second component, 4 plus 3t in the third component, or we could rewrite it as x equals 1 minus 6t, y equals -3 plus 4t, and z equals 4 plus 3t. And remember, because this is a line segment, our t value is restricted, and in the case of how we're doing this, it's going to be restricted from 0 to 1. If you wanted to use that shortcut, how that would work is you would have your vector function r equal to 1 minus t times r naught. So the vector pointing at the initial point, 1, sorry about that, -3, 4. Need a little more space here, plus t times the vector or the vector pointing at the point where we end, -5, 1, 7. And if you do some work, you will see that this gives us the same thing. So we take 1 minus t, we multiply that to 1, so that's 1 minus t. We're going to add that to -5t in that component, giving us 1 minus 6t, just like we had before. Taking 1 minus t, multiplying that to -3, so that's -3 plus 3t, and we're going to add that to this other vector, which has a t in that component, so that would be -3 plus 4t. Similarly, for z, we would get 4 plus 3t, where our t is defined from 0 to 1, giving us the same thing. I'm not going to write the x, y, and z, but those are the same with our same domain restriction. Okay, example number 5. We're going to find the vector function that represents the curve of intersection of the cylinder, x squared plus y squared equals 1, and the plane y plus z equals 2. So this gives us our visual of what I'm asking. Think about our circular cylinder. We're going to have a plane, and we want to know where they intersect. And mine is colored. You can see this red ellipse-looking path right there. That is how these two surfaces are going to intersect. Remember, the cylinder is not filled in, so it's just something that is going to be on the surface of the cylinder, and it's going to be where that touches the plane. So this picture over on the right gives you the visual of this intersection, and we can see that it is curved. It's not just a line. So last chapter we found the intersection of two planes, giving us a line. Now we have the intersection of a plane and a surface. So how are we going to do this? Well, here is what we're going to think about. We're going to start with the projection of our curve C onto the xy plane. Think about this red curve right here. If you were to look at it directly from above down the positive z-axis and look at how it casts a shadow on the xy plane. Ooh, I can't spell plane, can I? Sorry about that. that is going to be the circle, x squared plus y squared equals 1. Now, we have to come up with a way to parameterize this because we're trying to write a vector function that is based upon one variable. So when we have an equation right here with multiple variables, we got to parameterize this. So we need to think of functions that we could make x and y so that it fits this equation, but it's based upon only one variable, our parameter t. If you're ever dealing with circular things or elliptic things, the easiest way to parameterize this, and it's very similar to what we're doing in polar functions and polar equations, that is a parameterization, is we're going to call one of them sine, one of them cosine. Naturally, we call x the cosine, so we're going to say x is cosine t, y is sine of t, and to get around that circle once, we just need t to go from 0 to 2 pi. There's a different, like we could have used a different number next to t right there, and the value that t would have been restricted by would have been different, because if we would have done cosine of 2t and sine of 2t, then we would have only needed t to go from 0 to pi. So depending on how we write our functions, that will dictate how we're parameterizing it, how much our parameter is needed to change what its domain needs to be to get the full thing that we need. So how are we supposed to get the whole vector function? Because this gives us the first two components. And we do have to think about what we just came up with for our parameterization of x and y isn't the thing that's floating in 3 space. It's just on our two-dimensional plane. So what you're going to do is think about this. We have where this thing is intersecting y plus z equals 2. And we need to know what z is to write our vector function, so it might make sense now that z can be thought of as 2 minus y. And we have a way that we're already parameterizing y. So z can be represented by 2 minus sine of t. Therefore, putting it all together, our vector function r of t can be written through our parameterization of cosine of t, sine of t, and 2 minus sine of t, where t is defined from 0 to 2 pi. So that is the parameterization of our space curve. That gives us the vector function. You plug in different values of t, we will go around that looks like a kind of slanted ellipse through 3 space. So that is our vector function. Notice it's defined only through one variable. We have 3 components, but it's defined through only one variable. We plug in one value of t, and we get vectors which point at points. Okay, so getting a little bit away now from our space curves, we're going to do some calculus on vector functions. Limits and continuity. How much have you missed this? I know the answer is so much. So over this video and the next one for tomorrow's stuff, I'm going to show you how to find the limits of vector functions and the derivatives of vector functions. And as you might imagine for these, it is pretty straightforward. So the limit of a vector function r is defined by taking the limits of its components. So if you want to take the limit of some vector function r as t goes to some value, all you're going to do is the limit component-wise and see how that goes. This is provided that the limits, notice that is plural, the limits of the component functions exist. So the limit for the vector function exists only if all the limits of the components exists. If you remember your continuity definition from Calculus 1, this will not surprise you. We say a vector function is continuous at some value a if the limit of the vector function as t approaches a is the same as the value of the vector function when you plug in a. A more useful way of thinking about this definition above is that r is continuous at a if and only if its component functions f, g, and h are continuous at a. So the big question is, do you remember the continuity requirements from Calc 1? I went over this a few weeks ago with my VC class. I'm hoping you remember. A function f of t is continuous at t equals a if and only if three things happen. F of a is defined. The limit as t approaches a of f of t exists. And finally, the limit as t approaches a of f of t equals f of a. So that is our definition of continuity from last year. So how do you prove if something is continuous? You find the value of the vector function at wherever you're trying to test for continuity. You find the limits of all the components and make sure that the limits of all those components equal the components of the vector where you plugged in a. So our first example, we're going to find the limit as t goes to 0 of r of t, where r of t is defined as t squared I plus e to the tj minus 2 cosine of pi tk. So the limit as t approaches 0 of our vector function r is going to be equal to the limit as t approaches 0 of t squared. I'll put that in a set of brackets right there. I plus the limit as t approaches 0 of e to the t j plus, I guess I could do minus whatever, limit as t approaches 0 of negative 2 cosine of pi t k. So I'm just going to plug in the limit value into all of those because it doesn't look like we get any indeterminate forms. So that becomes 0i plus e to the 0 is 1j. Cosine of 0 is 1. Multiplied by negative 2 is negative 2k. So our limit can be represented as the vector 0, 1, negative 2. Or you could leave it with the I, j, and k if you'd like. Those are the same thing. So that is the limit. So notice now our limit isn't just a value. The limit is a vector. And each of the components is a value. Is r continuous at t equals 0? Justify your answer. You don't have to use the limit definition for continuity right here if you don't want to, as long as you give me something like this. We can say yes because f of t equals t squared, g of t equals e to the t, and h of t equals negative 2 cosine of pi t are all continuous at t equals 0. I assume that you know that all three of those are continuous functions, so you can tell me if you know this to be true, that the vector function will be continuous at a point because you know all of the components are continuous at that point. All right, so we got one more example here to wrap up 13.1. We're going to find the limit of r of t where r of t is a little bit more of a complex function. So let's write this down. The limit as t goes to 0 of r of t can be thought of as, I'm going to write my components here with limits. So limit as t goes to 0 of 4t cubed plus 3 over 3t cubed plus 1, comma, limit as t goes to 0 of 1 minus cosine of t over t, comma, limit t goes to 0 of ln of t plus 1 over t. First thing you should always try to do when taking limits is trying to plug in the number. We get 3 over 1, comma, 1 minus 1, we get 0 over 0, and 0 over 0. Lucky for us, I'm not College Board. You're welcome to write equals 0 over 0 now. I don't care. It's our indeterminate form. I'm expecting you remember how to evaluate these limits, because if you get the indeterminate form, that doesn't mean it doesn't exist. That means you have to try something else. And what is our something else going to be? It's going to be L'Hopital. So let's look at this. What is the limit as t goes to 0 of 1 minus cosine t over t? Because we get the indeterminate form 0 over 0, we're going to take the derivative of the top and bottom. We're going to do the limit as t goes to 0 of sine of t over 1, which is 0. Do you notice that I'm writing my limit notation correctly? If you don't, I'm going to take away points. For the other components where we get the indeterminate form, limit as t goes to 0 of ln of t plus 1 over t. Take the derivative of the top and bottom individually. We get 1 over t plus 1 over 1. That is 1 over 1, which is 1. So what is our limit equal to? The limit as t goes to 0 of r of t is going to be 3, 0, 1. All right, last example for this section is our continuous at 0. Justify your answer. Well, again, we could try limits, we could try to do that kind of thing, but think about this. Can we plug in 0? We tried to plug in 0, it didn't work. So the answer is no. Because if I keep calling it g of t equals 1 minus cosine of t over t, and h of t, which equals ln of t plus 1 over t, are both not defined at t equals 0. So those two functions don't exist at that point, so it can't be continuous. All right, depending on if you watch this at normal speed or half speed, you should have some time. You can start looking at your 13.1 WebAssign. Try that out. I will see you after the weekend, folks.